Flipped classroom video for Maths A2 Unit 3, Further Partial Fractions. We've looked at linear factors for our denominator, so we did two linear factors multiplied together for the denominator and three linear ones. But we might have a squared denominator, and that's a bit trickier. This first bit's called still worth working on, and it's because this is a rational expression with just a squared linear factor for the denominator. And when we look at it, we might think there's not a lot we can do with this. X plus 3 over x plus 2 squared, well, that's okay, looks pretty tidy. But we would like to be able to simplify it if we can. One motivation for this is it looks like it might be a bit tricky to integrate. So it's worth having a little play with it at least. So let's have a look. What we're aiming for is only numbers in our numerators. It depends how far you've got with your integration, but if we have just numbers over some sort of linear function or linear squared, we can handle those with integration. What we do is we think about it this way, that we can decompose it into something over x plus 2 plus something over x plus 2 squared, and the somethings, the a and the b, can be just numbers in this case. So we'll just press on and see what happens. We can use the method of comparing coefficients. If we multiply through by x plus 2 squared, we get x plus 3 is the same as a times x plus 2, because obviously only one of the x plus 2 squareds cancels with the x plus 2 on the bottom of the a over x plus 2 fraction, plus the b, the x plus 2 squared cancels away altogether. This gives us, for x, we have 1 equals a, so that's nice and easy. And for the constant, we have 3 on the left-hand side is equal to 2 times a plus b. And a little bit over the top with numbering this for students at your level, but never mind, it may help one or two. If we substitute the value for a into the second equation, we get 3 equals 2 plus b, and therefore b equals 1. Put them back in and we have this, that x plus 3 over x plus 2 squared is the same as 1 over x plus 2 plus 1 over x plus 2 squared. Is there a neater method? Well, we could do it this way. We could say, well, if we look at our x plus 3, if we turn that into x plus 2, that bit will cancel and that will leave us with 1, so x plus 3 is the same as x plus 2 plus 1, and that way we could just separate it out like this. So we'd have x plus 2 over x plus 2 squared plus 1 over x plus 2 squared, and that would give us 1 over x plus 2 plus 1 over x plus 2 squared, and that's of course the same as what we had before. So that's another way of looking at this. Now, if we have squared ones with linear ones as well, so something like this, then we need to keep in mind the previous example. So the x minus 1 is easy enough, that's just going to be a constant over x minus 1, and then the x plus 2 squared, as in the previous example, we break that up into something over x plus 2 plus something over x plus 2 squared. So altogether we have these three terms. Whatever method we use, we are first, as for all the previous examples, we're going to multiply by the left-hand side denominator. That will give us 9x plus 9, of course, on the left-hand side. On the right-hand side, I've just multiplied it through so we can see what happens and have a look at that quite carefully. The first term, the x minus 1 will cancel, so we're just left with a times x plus 2 squared. The second term, one of the x plus 2's will cancel, leaving us with an x plus 2 and an x minus 1. And for the third term, both of the x plus 2 squared terms will cancel, of course, because we've got x plus 2 squared on the top and the bottom, leaving us with just the x minus 1. Now we can proceed with either comparing coefficients of powers of x or substituting values in to eliminate one or more of the constants we're trying to find. And different people prefer different methods. If we compare coefficients, we can probably read them off by just looking at these, because they're not difficult to multiply out. X plus 2 squared is x squared plus 4x plus 4, so we could say for the x term we're going to have 4x in the brackets, therefore 4a. But actually it's much safer just to multiply it all out, and then you can read them off nice and easily. So this gives us 9x plus 9 is the same as a times x squared plus 4x plus 4, which is x plus 2 squared. Then we've got x plus 2 times x minus 1, which gives us x squared plus x minus 2. And then we have c times x minus 1. And then if we gather our different parts, we've got for x squared we have a plus b. For x we've got 4a plus b plus c. And for the constant we have 4a again minus 2b minus c. Therefore, let's lay this out. We've got x squared. On the left hand side we have none of them. On the right we have a plus b. For x we have 9 on the left hand side and our 4a plus b plus c on the right hand side. For the constant we have 9 on the left and 4a minus 2b minus c on the right. So we will label them 1, 2 and 3. And first of all we're going to put equation 1 into equation 2, and of course a is actually equal to minus b, or b is equal to minus a. So we will replace the b that's in equation 2 by minus a, and then tidy up, and that gives us equation 4. So we've now got 9 equals 3a plus c. We'll also put equation 1 into equation 3, and that will give us 9 is 4a minus 2 times the b, which is minus a, plus c. Tidy that up, and we get 9 equals 6a minus c. And of course what we've done now is we've eliminated b from 2 equations, so now we have 2 equations, 4 and 5, with 2 unknowns. Obviously we can solve them. If we add those two together it gets rid of c, so that gives us 18 equals 9a, and therefore a is 2. If we put 2 back into equation 1, that gives us that b is minus 2, and then if we put the a equals 1 into equation 4, that gives us 9 equals 3 times 2 plus c, which is 6 plus c, and therefore c is 3. Okay, now there is the alternative method, of course, of substituting values, so we'll save the writing out of the final answer for when we've had a look at that. Okay, so alternatively we could try substituting values in. If we put x equals minus 2 in, then the first term will disappear because a times x plus 2 squared will be 0, and the second term will disappear as well because b times x plus 2 times x minus 1 will also be 0. So what we'll be left with is 9 times minus 2 plus 9 is equal to c times minus 2 take away 1. And that gives us minus 9 equals minus 3c, and therefore c equals 3. If we put x equals 1 in, we're also going to get rid of 2 terms. We'll get rid of the b term and the c term because they're both being multiplied by x minus 1, which, when we put 1 in, will be being multiplied by 0. So that gives us 9 times 1 plus 9 equals a times 3 squared. The reason it's 3 squared is we've got x plus 2, and with x being 1, that is of course 1 plus 2, then squared. So that means we have 18 equals 9a and a equals 2. Now we've put the two possible values in that will make things 0, and we could now put another value in. We could put, for example, a equals 0 in, and that would mean we would have 4a minus 2b minus c equals 9, which is one of the ones we had from before. There's the calculation, which you can pause and have a look at if you like. But in some ways it's perhaps simpler at this point to just consider the coefficient of x squared. What we've done with the putting 0 in is we're considering the constant if we compare it to the previous method, but actually we can do the x squared very simply by just having a look at it. We can see that there are no x squareds on the left hand side, and on the right hand side we can see we've only got a plus b. So that gives us our 0 equals a plus b, and because we already know that a is 2, b is minus a, and therefore minus 2. So you can see that the substituting values in is a nice quick method. With all of this, you've got to be careful. This is quite complicated algebra. There's a lot of stuff going on, so writing things down is important, particularly at first. You may get quicker and more able to sort of spot things, but I would definitely recommend writing all your working out at first. Anyway, it'd be nice to see the final result, and here it is. 9x plus 9 over x plus 2 squared times x minus 1 is the same as 2 over x minus 1 plus minus 2 over x plus 2 plus 3 over x plus 2 squared. And notice we could have written it 2 over x minus 1, take away 2 over x plus 2 plus 3 over x plus 2 squared. It doesn't really matter which way you write that. Now all the rational expressions we've been looking at have been proper rational expressions. Proper meaning that the degree of the polynomial on the top of the fraction is less than the degree of the polynomial on the bottom of the fraction. But we might have to deal with what are called top-heavy fractions, or what we can call top-heavy fractions. So these are improper fractions. They have a higher degree on the top than on the bottom, or perhaps the same degree. But the example we're going to look at does have a higher degree. We've got a degree 4 on the top. The highest power of x is 4. And on the bottom, if we multiply that out, you can probably see that we would get a cubic. So that would have a highest power of 3 on the bottom. So we have an improper rational expression. The first thing we do with this is we multiply out the denominator. And now we could divide the numerator by the denominator and then find partial fractions for the remainder, or we could gradually strip out the parts of the numerator that we don't want. So let's have a look at the method here. Our f of x, and notice this time I have said f of x is equal to this rational expression because it saves covering a lot of the screen with just writing it out again. So f of x is going to be something over x cubed minus 3x plus 2. Now let's have a think about the x to the power of 4. If we want to be able to cancel somehow the x to the power of 4, then x to the 4 is x times x cubed. So what we can do is we can times the denominator by x, which will give us our x to the 4. It will also give us minus 3x squared and plus 2x. But that means we know we'll be able to cancel that away at some point. So that means we have, in the future if you like, we are prepared now to deal with that x to the power of 4. However, we need to work out the rest of the expression. So we've got plus 3x cubed. The original numerator had 3x cubed in. We haven't changed that with our little move of putting x to the 4 minus 3x squared plus 2x. So we still need our 3x cubed. For x squared, we want minus 2x squared, and so far we've got minus 3x squared. So that means we need to add an x squared in to make that match. For x, we have plus 2x so far, but we need 5x, so we're going to add 3x. And for the constant, we had minus 3 originally, we need minus 3, so there's our minus 3. So what happens now is those first three terms, the x to the 4 minus 3x squared plus 2x, will cancel with the denominator to just give us x. So we've now got f of x is x plus 3x cubed plus x squared plus 3x minus 3 over x cubed minus 3x plus 2. Now we've still got an improper fraction because we have the degree of the numerator is the same as the degree of the denominator, and we need it to be less than. So we're going to do the same thing again. We're going to say that f of x is x plus something over that fraction. Now for the 3x cubed, if we just write 3 times the denominator, that's going to give us our 3x cubed. It's also, though, given us minus 9x and plus 6. So we've got to be careful to make sure we deal with those properly. The x cubed term from before is dealt with, that's fine, we've got 3x cubed. We need an x squared, so we'll add an x squared in. For the x term, as I said, we've got 3 times minus 3, which is minus 9x, but we want plus 3x, so we'll need 12x to make that up. And for the constant, we've already got 6 now, 3 times the plus 2 from the bracket, and we want minus 3, so we're going to have minus 9. So now the top of that fraction equals the top of the fraction on the previous line, and we can now break that up. We've got our x, which we had before. We now have 3 times the denominator, which becomes 3 when divided by the denominator. And what's left over is x squared plus 12x minus 9 over x cubed minus 3x plus 2. And we can then write the denominator back in the form of the original function. So we've got x plus 3 plus x squared plus 12x minus 9 over x plus 2 times x minus 1 squared. Now, you can have a go at finding the partial fractions for the rational expression part of this using one of the methods that we've looked at previously in this video, but what this screen, if you like, has shown is how to deal with a top-heavy fraction by stripping away the bits we don't want, which in this case were the x to the power of 4 and the 3x cubed. Once we've stripped them away, we're left with a proper rational expression which has a degree 2 on the top and degree 3 on the bottom in this case, which we know how to deal with previous methods. If you do want to have a go at it yourself, then you should pause and do that, because I'm now going to show you the answer for completeness, which you can compare to yours if you sensibly have a try at it. And it's a bit of a mad one, but here we are. We have that f of x is equal to x plus 3 minus 29 over 9x plus 2 plus 38 over 9x minus 1 plus 4 over 3x minus 1 squared. And if you haven't had a go at it, you should perhaps ask your teacher to show you on the board.